As promised, we're going to head into frame relay now, and we have plenty of labs in this section as well, including some important debugs. We're going to talk about the theory of frame for just a few minutes and talk about what exactly it is, because point-to-point networks are pretty nice. HDLC, nothing to it, not a lot of protection there, but nothing else to it. And PPP, easy to configure, easy to troubleshoot. Well, they're nice, but there's a real limit to scalability. It is just not practical to build a dedicated link between every single router in our network, and it's not real cost effective either. It would be much easier and much cheaper to share a network that's already in place, and that's where frame relay comes in. A frame relay network is a non-broadcast multi-access network, NBMA. The non-broadcast part means that broadcasts are not transmitted over frame relay by default, not that they can't be sent. We're going to see that in our labs. Multi-access refers to the fact that the network will be shared by multiple devices. Now, the frame provider's collection of frame switches has a rather curious name. It's gotten a lot more commonplace since we have the cloud out there. But a frame relay cloud is what we're going to have between our endpoints. And you'll often see those frame provider switches represented with a cloud drawing, much as this, and I've got some other ones for you in this section as well. There are two kinds of equipment overall in this network. Now, the frame switches, the data communications equipment in this particular instance, these belong to the frame provider. We don't have anything to do with their configuration. So they're DCEs, but we don't have anything to do with them. The routers are the data terminal equipment, the DTEs, and as you know, we have a lot to do with their configuration. Now, each router is going to be communicating with a frame relay switch via a serial interface connected to a leased line, and the DCE must send a clock rate to that DTE. And we've already seen what happens when that doesn't happen. If the clock rate isn't there, the line protocol is going to go down. Your DCE always has to supply a clock rate to the DTE. Now, these two frame switches are hardly going to be the only switches in the cloud. We could have dozens, we could have hundreds, we could have thousands. We're going to have a lot of frame switches in there. And the thing is, our data from point A to point B is most likely going to take a different path through the cloud every time. And you and I, as network admins, we don't need to list every possible path in the cloud because, frankly, you and I don't really care. That's not our domain of influence, so to speak. We're not in charge of that. The key here is to know that not only will there be multiple paths through the cloud from any point A to point B, but the data probably will take different paths through that cloud. That's why we call this connection a virtual circuit, a VC, and we're going to talk about a permanent virtual circuit and a switched virtual circuit in just a moment. But the key with the virtual circuit term, we can send data over the cloud anytime, but data is not going to take the same path through the switches every time. Frame relay is referred to as a packet switching protocol. And that refers to what I've been hammering you over the head with for the last minute, that the packets may take different physical paths to get where they're going, and then they'll be reassembled and take the form of the original message. Circuit switching protocols have dedicated paths for data to go from point A to point B. Now, about those two types of virtual circuits, one is much more popular than the other. A permanent virtual circuit, it's available all the time. A switched virtual circuit is up only when certain criteria are met. Now, you're going to see PVCs in most of today's networks, and that's what's on the CCENT and the CCNA exam, and that's the kind of virtual circuit we're going to work with throughout this section. I'm going to tell you what an SVC is, but we are not going to configure it. It can be appropriate, though, when data is rarely exchanged between two routers. Now, the reality is that frame is so cheap, and permanent virtual circuits are so cheap, the providers would actually rather you use PVCs. So, and it's rare, but on occasion you could have a remote site, and I've worked with these before, where they literally only communicate with the hub of the network 5 minutes a week. They have to send a little bit of data out there, a little bit of payroll data in, who knows, once a week, something like that. Well, in that situation, an SVC may be more cost effective than a PVC. You know what an SVC is? It's really an on-demand virtual circuit because it's built when it's needed. Certain criteria are met, and we're sending data to this destination, therefore go ahead and build the VC. and it's torn down when that need ends. And of course, that would likely be when data hasn't gone over the VC for a certain period of time, the SVC would be torn down. Now we have two kinds of virtual circuits, and in turn, a PVC can be used to build a full mesh or a partial mesh network. Now a full mesh is where every router has a logical connection to every other router in the frame relay network. Now the problem with full mesh networks, even if you haven't already seen it on the screen, you can see that this is not a scalable solution. If you added one router to that network, you'd have to go to every one of those routers and add a virtual circuit to the new router, and sooner or later something's going to get botched up with that. It's just not a scalable solution. Now, with dedicated leased lines, full mesh networks aren't terribly scalable. A dedicated line is even worse. You're not going to put a dedicated line between every router in a 20 router network. It's not going to happen. Much more common is the topology we're going to work with in this course, and we're going to build one of these from scratch. It's a hub and spoke network. It's a partial mesh topology. The first thing I want you to know, and I am going to hit you over the head with this pretty often, but it's vital to remember, when in a hub and spoke network, any spoke to spoke communication goes through the hub. The spokes don't have a logical connection to each other. That's where the spoke term comes from. It's like a spoke out there by itself. Now, you could see where this would beat the heck out of dedicated lines, especially as your network grows. If you added 7 more routers or 17 more routers, you would just need to create a VC between the hub and each one of your new routers. Because the more connections you get, I can't even imagine having a full mesh huge network. There's just so much overhead to try to keep up with. Now with PVCs, particularly in a hub and spoke network, you could build this literally in minutes once your frame provider gives you the information you need to create your mappings. That would be it. It would be very quick. Now we're going to get to that information and the mappings very soon. Let's talk about the LMI, the heartbeat of frame relay here for just a moment. The LMI, it sounds like a GUI, or it sounds like some kind of server. Well, this is the local management interface. Well, these are the messages, the LMI messages that are sent between the DCE and the DTE. Please note that they're both sending them. It's not a one-way deal. Now, the management part of that refers to the PVC management and info regarding your addressing, multicasting, and virtual circuit status, whether it's up or down, or it even exists. It's actually contained in the LMI. Now, a particular kind of LMI message, it's the LMI status message. We're going to see this with a debug in just a few minutes. This serves as our keep alive for the logical connection between the DTE and the DCE. If these keep alives are not continually received by both parties, what's going to happen? The line protocol is going to drop. This is something else that can make our line protocol drop. We've seen a couple of those already. But with frame relay, in the absence of the LMI message that is expected, then, then our line protocol can go down. The LMI types have to match on the DTE and the DCE for the PVC to be established. And there are 3 types of LMI. Cisco, which is the default and occasionally referred to as the Gang of 4 LMI, sounds a little threatening, but it's really not. We have ANSI and we have Q933A. And the Gang of 4 term simply refers to the 4 vendors that were involved in its development. It was actually Cisco, Stratacom, DEC, and Nortel. Now, we can change the LMI type with the frame relay LMI type command, and we're going to do that on the live equipment here in just a few minutes. But before we do anything like that, we have to enable frame relay on the interface with the encap frame relay command, because we know the default encapsulation type is what? It's HDLC. So if we're using anything else, we have to manually change that. Now, LMI AutoSense, this is an interesting feature. It takes effect when you do not specify an LMI manually. When you open the interface, LMI AutoSense has the router send out an LMI status message for 3 LMI types, all 3 of them, one for Cisco, one for ANSI, one for Q933A. Then the router waits to hear back, and it's only going to hear back to one of those LMI types. And when the router sees the response to its LMI AutoSense messages, the router will then send only the same LMI type it received from the DCE. So at the beginning of the process, 3 LMI go out, 1 comes back, and from then on, it is hopefully an even exchange. Now, the frame relay LMI, This isn't exactly something we change on a regular basis. So once it's up and running, the mismatches are pretty darn rare, but we want to make sure we can spot one. And we're going to create an LMI mismatch here in a moment. And we're going to use our first debug on Frame Relay. And I know you're thinking, okay, we haven't built Frame Relay Lab yet. How are we going to debug anything? Well, we are going to go through several full Frame Relay Labs in this section, 2 of them where we're building everything from scratch. But I want to show you the LMI info now while we're talking about it. I don't want to talk about it and then come back to it 30 minutes later with an example. So to that end, I have created a working Frame Relay network, which we're going to debug, and we're going to throw a little monkey wrench in there. And then we'll see what happens when we have an LMI mismatch and exactly how to spot one. There's a good show command and a good debug command for that. And you'll see both of them in the very next video. See you there.